This is your presenter Asloob Mudassar, and I am presenting slide number 47 of the course on laser physics. Question is, find an expression for the normalized spectral density function of the incident radiation represented by g of nu prime minus nu, which appears in the expression of transition probability in equation number 46.1 due to collision broadening. So here we have to find out the expression for g of nu prime minus nu, which is the normalized spectral density for the incident radiation. The answer is, let tau is the time interval between two consecutive collisions, which will differ from collision to collision. That is, tau will have some distribution. Let us represent this distribution by a probability density represented by p tau, defined by p tau is equal to 1 over tau c multiplied in the numerator by e to the power minus t over tau c, as given in equation number 47.1, where tau c is equal to the average value of tau given by the integral from 0 to infinity tau into p tau, and the integral is with respect to d tau, as shown in equation number 2. So this tau c is the average time between collisions. Now we want to connect g of nu prime minus nu with the electric field of the incident light. Wiener-Khinchin theorem states the Fourier transform of the autocorrelation function gamma of tau of the signal E of tau gives the power spectrum W of omega prime minus omega of the incident signal. So you see that here we are declaring gamma of t as the autocorrelation function of the signal E of tau, where E of tau is the electric field of the incident beam. So gamma is the autocorrelation of the electric field of the incident beam. So once we have the gamma determined, then the Fourier transform of this gamma will give you the power spectrum, and that power spectrum is represented by capital W as a function of omega prime minus omega, and this is stated over here as in equation number 47.3. So you see that we have capital W as a function of omega prime minus omega, and on the right hand side we have the integral. This integral is actually the Fourier transform integral. So it means that this integral represents the Fourier transform of gamma of tau. And you see that the Fourier parameter over here is e to the power minus iota omega prime tau, and the integral is with respect to d tau. The limits are from minus infinity to plus infinity. So the integral on the right hand side is actually the Fourier transform of gamma of tau, where gamma of tau is defined as, since we have declared over here that is gamma of tau is nothing but the autocorrelation function of the signal E, and E is the electric field of the incident beam. So we can write gamma over here, that is gamma of tau is equal to the limit as t goes to infinity, then 1 over 2t, and the integral from minus t to plus t, and then you see that this integral is nothing but the autocorrelation function, in which we have taken the complex conjugate of one quantity multiplied by the time delayed function or of the other function, that is E star, which is the complex conjugate of E star of t multiplied by E of t plus tau, and the integral is with respect to dt. So this is the definition of the autocorrelation integral, and you see that we have represented gamma as the autocorrelation of the electric field of the incident beam, as shown in equation number 4. Here E of t is the electric field in the presence of collision as seen by the atom. So we can represent E of t as E naught into e to the power iota, within the parentheses we have omega t plus phi of t. Omega t is the frequency of the incident beam, and where phi of t is the time varying phase due to collisions with atoms. Now we connect capital W, which is a function of omega prime minus omega, with g of omega prime minus omega, and ultimately with g of nu prime minus nu through the relationships. So So we have this relationship given in equation number 6, which is g of nu prime minus nu is equal to 2 pi of g of omega prime minus omega is equal to capital W of omega prime minus omega. And you know that this capital W has already been defined in one of the previous slides, which is the transition probability or the transition rate. And you see that we have also defined the function g earlier in one of the slides. So g of nu prime minus nu obeys normalization condition, which we have also discussed previously. So let me reproduce this normalization condition over here. So we have g of nu prime minus nu integrated between the limits from minus infinity to plus infinity with respect to d nu prime is equal to 1. So you see that when this integral g of nu prime minus nu is normalized, then the other functions on the right hand side, that is g of omega prime minus omega and capital W of omega prime minus omega, should also be normalized. So let's extend this normalization condition to the other functions also. Thus g of omega prime minus omega and capital W of omega prime minus omega will also obey the similar normalization conditions. Let us find E naught using the normalization condition as given. So we are using the normalization condition, which is shown over here, that is capital W as a function of omega prime minus omega integrated with respect to dw prime within the limits from minus infinity to plus infinity is equal to 1. And you see that here we have to use the values of this W, capital W, from the previous equations. That is from this equation. So we can substitute capital W in terms of the integral in terms of gamma of tau. And you know that this gamma of tau is given by equation number 4 over here in terms of the autocorrelation function of the electric field of the incident beam. So it means that we have to solve this integral, we have to solve gamma of t for in equation number 4. Then we have to plug in the value of gamma of t in the integral shown in equation number 3, and then we have to substitute this value of capital W in this equation over here. And then we have to solve all these integrals successively. That is, first you will solve capital gamma of tau using the electric field shown in equation number 5. So submit E of t from equation number 5 into the right hand side integral in equation number 4. Then solve gamma of t. This should give you E naught mod square multiplied by e to the power iota omega tau, and some phase value e to the power iota phi of tau. So that will be substituted, that value of gamma will be substituted in this integral. Then this integral will be solved, and this capital W then will be substituted in this integral. Then you will get the answer, and the answer of all these integrals that we solve will be equal to 2 pi into E naught square. So from here we can get the value of E naught square is equal to E naught square is equal to 1 over 2 pi. Actually this please make a correction that this is E naught, not E naught square. So this is E naught is equal to 1 over square root of 2 pi, or otherwise you can say that E naught squared is equal to 1 over 2 pi. So please make a correction over here. The integral in equation number 47.4 may be expressed as, so we can express the integral, that is this integral over here. Let's interpret this integral in some way. So we can write this integral in equation number 4 in the following form, that is gamma of t is equal to the limit when t goes to infinity, and then we have E naught square e to the power iota gamma or iota omega tau divided by 2 capital T, and within the parenthesis and within the curly brackets we have two integrals. One integral has the integrand as a correlated signal, the other has uncorrelated signal, both integrated from minus capital T to plus capital T with respect to dt. So we have named, that is we have split the integral over here in equation number 4 in terms of the two integrals. that is in terms of the correlated signal and in terms of the uncorrelated signal. When the signals E of t and E of t plus tau are correlated, they have the same phase, and when they are uncorrelated, they differ by a random phase. The integral with the uncorrelated signal vanishes, whereas the integral this one gives the total time of phase correlation, that is the sum of all the phase correlated time intervals. So at least one of the integral will vanish out over here, and the other integral, that is the integral which we have shown in blue color over here, gives the total time of the phase correlation, that is the sum of all the phase correlated time intervals. And you see that we have regarded this one, that is for integral from minus t to capital T is equal to or integrand is correlated signal, integration is with respect to dt, and we have approximated this one is equal to sum over n, and within the we have the argument as t n prime tau n prime minus tau. So let me go back to this equation. You see that what we want to determine in this equation, we want to determine actually g of nu prime minus nu. This is what we want to determine. We want to determine an expression for the value of g of nu prime minus nu. And you know that to determine this one, we shall determine capital W of omega prime minus omega. So once this is determined, it means that g of nu prime minus nu will also be determined because of this expression. Okay, now let's go back to this integral where we have substituted, where we have assigned the value, that is the integral under correlated signal is equal to summation n, and the arguments are tau n prime minus tau, where tau n prime is the time interval between the nth and the n plus 1 and the n plus 1 and the n plus 1th phase jumps. So time interval between nth and n plus 1th phase jumps, and the tau over here is the time interval during which the signals are uncorrelated. Thus tau n prime minus tau is the time interval during which the signals are correlated. That's why we have represented the correlated signal argument in the integral by tau n prime minus tau, because the difference of these two actually gives you the time interval during which the signals are correlated. Thus, we have gamma of tau from this equation, where the integral over the uncorrelated signal will vanish to 0. And we have also substituted the correlated integral by the value of this summation. Then using these summations, we are writing gamma of tau is equal to the limit tau goes to t goes to infinity e naught square into e to the power iota omega tau divided by 2t, and the integral is over correlated signal from minus capital T to plus capital T. And this integral has been substituted by this summation sign which we have used over here, shown in red. So we have taken some terms which are independent of the limit, and that is the e naught square e to the power iota omega tau, and the limit will be applicable to this term because we have capital T in the denominator of this expression. Let's introduce capital N as the number of phase jumps between minus capital T and plus capital T. So these are the number of phase jumps. So let's divide the numerator and the denominator by capital N. The numerator can now be written as the average value of tau prime minus tau, and the denominator can be represented by tau c, where the average value of tau prime minus tau is the average value of tau prime minus tau, where the tau prime is greater than tau. So to compute the average value of tau prime minus tau, we use equation number 47.2. So let me show that equation. this equation. So the average value, to find the average value we shall use the equation given in 2. So this is what we have used equation number 2 to give to find out the value of the average value of the t prime minus t, and the argument in the integral has been replaced by tau prime minus tau, and the rest of the quantities are the same as defined in equation number 2, which is p tau prime, and the integrand and the integral is with respect to d tau prime. So we have substituted the value of p tau prime from equation number 1, that is from this equation. We can use the value of p tau prime is equal to 1 over tau c multiplied by e to the power minus tau over tau prime over tau c. So using this value from equation number 1, over here we have substituted the value of p tau prime from equation number 1 over here, and then solved the integral which is approximately equal to tau c multiplied by e to the power minus tau over tau c. So the average value can be written as the average value of tau prime minus tau divided by tau c, that is the whole value, that is the value on the right hand side which is shown in blue, that is given by, now the average value of tau prime minus tau divided by tau c is equal to e to the power minus tau over tau c. So now we have gamma of t is equal to e naught square into e to the power iota omega tau multiplied by e to the power minus tau over tau c. So we have combined the two exponentials, and then we have on the right hand side e naught square into e to the power iota omega tau minus tau over tau c. So we have found the value of gamma of t. Since gamma of t has to be symmetric, that is an even function, obeying the definition that gamma of minus tau is equal to gamma of tau, thus we can rewrite this as gamma of tau is equal to e naught square e to the power iota omega tau minus tau mod over tau c. We have taken the mod because both possibilities are there. That is as we have shown that it should be a symmetric function. That's why we have taken the absolute value of tau over there in equation number 7. Thus we have found t, now we can find w using the definition over here, because w, which is the probability, which is the transition probability or the transition rate, capital W as a function of omega prime minus omega, given by in terms of the Fourier transform of gamma of t. So we have found gamma of t. Now we can substitute the value of gamma t over here, and we can find out an expression for capital W. Over here in equation number 8, so we have substituted the value of gamma from equation number 7 into the previous equation as I have shown just a moment ago, and then substituting these values and then solving the integral, we have found the value of the capital W as a function of omega prime minus omega is equal to 2 tau c divided by 1 plus omega prime minus omega, the square of this quantity, and multiplied by the square of tau c, as shown in equation number 8. So now we can find out g of nu prime minus nu because of this relationship. Because we have found the value of capital W in equation number 6 in terms of, so we can also find g of nu prime minus nu directly from this relationship. So we have found capital W. So we can write the relationship that g of nu prime minus nu using equation number 6 is equal to 2 tau c over 1 plus nu prime minus nu, the square of this quantity, and multiplied by 4 into pi square into tau c square. Here we have used the fact that omega is replaced by 2 pi nu. So we have taken 2 pi factors separately, and we have shown this as a function of nu prime minus nu, because on the left hand side we have g of nu prime minus nu. So on the right hand side we have also shown nu prime minus nu, and the rest of the factors we have shown separately. So we have found an expression for the value of the function g of nu prime minus nu. And you see that if you look at the statement of the question, we have to find this function, that is find an expression for the normalized spectral density function of the incident radiation g of nu prime minus nu. So this is what we have found, and it is a normalized spectral density function of the incident radiation. So this expression is what we have found over here and is shown in equation number 9. This is the normalized spectral line shape of the incident radiation. Now we can also find out from this relationship the line shape of the transition. The line shape of the transition can be obtained from equation number 9 by replacing nu prime by nu naught. So if you put nu prime by nu naught in equation number 9, you will get g of nu naught minus nu. But I have changed the order of the argument because g is an even function. So here I have written g of nu minus nu naught is equal to the rest of the quantities. I have also, because it is a squared quantity, so I have also changed nu minus nu naught. And you know that I have also split this function into two forms, because I want to compare this function with some function else, which I am going to mention soon. So g of nu minus nu naught is equal to 2 over pi, and within the parentheses I have 1 over pi tau c, and then another the split, because I have splitted the function in the middle into two parts. The other part is 1 over 1 plus square of 2, within the square bracket we have 2, within the parentheses we have nu minus nu naught divided by 1 over pi into tau c. So you see that this is what we have found, an expression of g of nu minus nu naught. And this g of nu minus nu naught is actually the line shape of the transition. Okay. And why I have written this one? Because so that we can compare it with the Lorentzian line shape given in equation number question 36.15. In equation number 36.15. So we can compare this function g of nu minus nu naught with the Lorentzian line shape given in equation number 36.15, and then we can obtain the values, that the peak value by comparison is equal to 2 into tau c, and the line width delta nu naught is equal to 1 over pi into tau c. So you see that this is just a comparison that we have made at the end with the Lorentzian line shape obtained earlier. So our main task was to find out g of nu prime minus nu as given in equation number 9, and from here we have also found the line shape of the transition, which is given over here. And we have also made the comparison of this line shape of the transition with the Lorentzian line shape given in equation number 36.15. So this completes our answer to the question. So this is the end of slide number 47.